Evapotranspiration. So what is evapotranspiration? Evapotranspiration equals to evaporation from water surface and soil plus transpiration from vegetation. So as you might see here from this image, so water comes to the area through precipitation and runoff, and solar radiation transfers water into water vapor through transpiration from plants and grasses and trees, and evaporation from soil surface and water surface. And the rest of the water goes to groundwater area, groundwater, and through runoff. This is called water balance. Evaporation. Evaporation is a process whereby liquid water is converted to water vapor, vaporization, and removed from the evaporating surface, vapor removal. Water evaporates from a variety of surfaces such as lakes, rivers, pavements, soils, and wet vegetation. Energy is required to change the state of the molecules of water from liquid to vapor. Direct solar radiation and to a lesser extent the ambient temperature of the air provide this energy. The driving force to remove water vapor from the evaporating surface is the difference between the water vapor pressure at the evaporating surface and that of the surrounding atmosphere. Transpiration. Transpiration consists of the vaporization of liquid water contained in plant tissues and the vapor removal to the atmosphere. Crops predominantly lose their water through stomata. These are small openings on the plant leaf through which gases and water vapor passes. So this is a leaf, and there is an intercellular space here where water is stored, and it converted into water vapor through this stomatas, where energy reaches to this area, water through stomatas, and water just through vaporization process converts into water vapor. Evaporation and transpiration occur simultaneously, and there is no easy way of distinguishing between the two processes. Apart from the water availability in the topsoil, the evaporation from a cropped soil is mainly determined by the fraction of the solar radiation reaching the soil surface. So there is a graph here which shows the partitioning of evapotranspiration between soil evaporation and crop transpiration. As you may see here, at the beginning of the sowing process, the maximum of evapotranspiration occurs due to soil evaporation because there is no vegetation which covers the soil surface. Through the vegetation reaches its peak of leaf area index and peak of the biomass, most of the evapotranspiration happens due to this water, this plant transpiration. So approximately 70% of evapotranspiration happens due to water, this plant transpiration. Only 10% happens due to soil evaporation. When the plant is harvested and the vegetation is not so abundant, the difference between crop transpiration and soil evaporation becomes almost equal. So primary factors. Because evaporation and transpiration occur when water moves into the air, levels of evapotranspiration in a given area are primarily controlled by the existence of surface water, the abundance of energy, vertical heat, stored in the soil and in the atmosphere. So in hot areas, as you may see on this image, on the middle, the lots of heat is stored in soil and in the atmosphere. And the third one is the ability of the air to uptake water vapor, because if the air is very humid, as you may see here on this image on the right side, it's not able to uptake water from plants and soil because it's already very saturated. Secondary factors. Vegetation type impacts levels of evapotranspiration. So herbaceous plants are able to transpire less amount of water comparing to woody plants because they have less amount of foliage. Also, conifer forests in general have high level of annual evapotranspiration because they can transpire water, especially transpiration, because they comparing to deciduous forests because they are evergreen and able to transpire water to the air even during winter periods. Also, the availability of groundwater and the length of roots also depend on transpiration because plants with longer roots are able to reach groundwater surface, groundwater level, and uptake water and move it to the plants and leaves, and therefore leaves transpire more amount of water to the air. Also, comparing to those plants which have shorter roots. Also, the level of groundwater also impacts because lots of plants, lots with their roots, are unable to reach the groundwater surface and uptake water. So units are measured in millimeters per day, weeks, months, and year. So 1 hectare equals to 10,000 square meters, and 1 millimeter equal to 0.001 meter. So 1 millimeter of water loss per 1 hectare equals to 10 cubic meters of water loss per hectare. So 1 millimeter per day per hectare equals to 10 cubic meters of water loss per day per hectare. So to illustrate, let me show it as an example. So there is an area with with width of 15 hectares and length of 10 hectares. So in general, the area of this agricultural plot is 150 hectares. And if there is evapotranspiration rate per year is 500 millimeters, it means that 150, the area, multiplied to 500, the water loss, multiplied to 10 cubic meters because it's 1 millimeter per hectare is 10 cubic meters. So in general, this year, this area lost 750,000 cubic meters of water for this year. So it's a large amount of water. So also evapotranspiration can be measured in energy. So water depths can also be expressed in terms of energy received per unit area. The energy refers to the energy of heat required to vaporize free water. This energy, known as the latent heat of vaporization, is a function of the water temperature. So 20 degrees per Celsius equals to 2.45 megajoules per kilogram. So this energy is required to evaporate 1 liter or 0.001 cubic meters of water. So 2.45 megajoules per square meter is able to vaporize 1 millimeter of water from this meter. So let's calculate 500 millimeters per year of, in order to vaporize 500 millimeters of water for 10 hectares, we just multiply 10 cubic meters to 500 to 10 hectares of the area and 2.45 megajoules, which is able to vaporize 1 liter of water, and multiply to 1000. So in general, to vaporize 500 millimeters of water from 10 hectares, we need more than 12 millions of megajoules of energy. So as you may see here, this equivalence 1 millimeter per day is equals to 10 cubic meters of per hectare and equals to 2.45 megajoules of energy per day per square meter. Also 1 cubic meter of hectare per day equals to 0.1 millimeter per day. The same is to the volume, and equals to this energy per square meter to vaporize, etc. So in order 1 megajoule of energy per square meter per day is able to vaporize less than a half of millimeters of water per day, and this amount of energy 4 cubic meters, or not energy, water, 4 cubic meters of water per day per hectare, etc. So there is an example on this table. On a summer day, a net solar energy received at a lake reaches 50 megajoules per square meter per day. If 80% of the energy is used to vaporize water, how large could be the depth of evaporation be? So from the table, 1 megajoule per square meter per day equals to this amount of water. And if the 80% of the energy is from 50 megajoules is used to transpire water, to vaporize per day, we have this almost 5 millimeters per day of water. This amount of energy is able to vaporize. Potential evapotranspiration. Potential evapotranspiration is the amount of water that would be evaporated and transpired by a specific crop, soil, or ecosystem if there were sufficient water available. It is a reflection of the energy available to evaporate or transpire water and of the wind available to transport the water vapor from the ground up onto the lower atmosphere and away from the initial location. Actual evapotranspiration is said to equal potential evapotranspiration when there is ample water existent. Evapotranspiration can never be greater than potential evapotranspiration, but can be lower if there is not enough water to be evaporated, or plants are unable to transpire maturely and readily. So potential evapotranspiration is usually measured indirectly from other climatic factors, but also depends on the surface type, such as free water for lakes and oceans, the soil type for bare soil, and also the density and diversity of vegetation. So potential evapotranspiration. Potential evapotranspiration is high in the summer on clearer and less cloudy days and closer to the equator because of the higher levels of solar radiation that provides the energy, heat for evaporation. Potential evapotranspiration is also high on windy days because the evaporated moisture can be quickly moved from the ground or plant surface before it precipitates, allowing more evaporation to fill its place. Reference evapotranspiration. The evapotranspiration rate from a reference surface not short of water is called the reference crop evapotranspiration, or reference evapotranspiration, and is denoted as ET0. The reference surface is hypothetical grass reference crop with specific characteristics. The use of other denominations such as potential evapotranspiration is strongly discouraged due to the ambiguities in their definitions. The only factor affecting reference evapotranspiration are climatic parameters. Consequently, reference evapotranspiration is a climatic parameter and can be computed from just weather data. Reference evapotranspiration expresses the evaporating power of the atmosphere at a specific location and time of the year and does not consider the crop characteristic and soil factors. The Fauth-Penman-Monteith method is recommended as a sole method for determining reference evapotranspiration. The method has been selected because it closely approximates grass as the location evaluated, is physically based, and explicitly incorporates both physiological and aerodynamic parameters. Moreover, procedures have been developed for estimating missing climatic parameters. So this is a reference evapotranspiration. Here's on the top of the image. Climate, which includes radiation, temperature, wind speed, and humidity, and just a reference crop, which well-watered grass, which creates reference evapotranspiration. And the second image on the middle shows the crop evapotranspiration under non-standard conditions. For instance, it includes water and environmental stress. So what KS and KC adjusted. So you just multiply to adjusted factors non-standard conditions of reference evapotranspiration. and crop evapotranspiration under standard conditions, well-watered crop optimal agronomic conditions. See, this is ATC not adjusted. So measurements of evapotranspiration. There are three types of measurements to measure evapotranspiration. It's direct measurement, catchment water balance, and energy balance. So direct measurement. So evapotranspiration can be measured directly with a weighing or pen lithometer. A lithometer continuously measures the weight of a plant and associated soil and any water added by precipitation or irrigation. The change in storage of water in the soil is then modeled by measuring the change in weight. When used properly, this allows for precise measurement of evapotranspiration over small areas. Catchment water balance. Evapotranspiration may be estimated by evaluating the water balance equation for a given area. The water balance equation relates the change in water stored within the basin as to its input and outputs. So where you can see here the equation of evapotranspiration. So P is precipitation, minus S is water stored within the basin, minus Q is stream flow, and minus D is groundwater recharge. So the rest of the water goes to evapotranspiration. But in order to calculate the catchment water balance, you need to have all the information: precipitation, the water initially stored within the basin, how much water goes to stream flow, and how much water went to recharge, which is hard to measure. And the third one is the energy balance. So using this formula, evapotranspiration is a net radiation flux minus a soil heat flux minus sensible heat flux. Using instruments like a scintillometer, soil heat flux plates, or radiation meter, the components of the energy balance can be calculated and the energy available for actual evapotranspiration can be solved. The Sebal and metric algorithms solve the energy balance at the Earth's surface using satellite imagery. This allows for both actual and potential evapotranspiration to be calculated on a pixel-by-pixel basis. Sebal and metric can map these key indicators in time and space for days, weeks, or years.